Hi guys, and welcome to, I think we are in the 5th week now. Put this name on this side. We're on the 5th week and we are due for an exam that is coming soon, okay? So this is a very important part of the process. It's not posted already? It should have been. Oh man, probably I did not, I guess. Okay, hold on. That's a good question. Hold on, okay? Let me go back into the content in here. Astronomy 170. And last Thursday was, oh no. It was never uploaded. I never downloaded it. Okay, very good. Thank you, Susan, for reminding me of this, okay? I will upload it, okay? You guys need to remind me right away of it, okay, please. I know it's saved, but I did not really download it yet, and for some reason, and it's sidetracked, I guess. The question is about Thursday's session. The recording was not uploaded to Canvas, so I'm going to do it hopefully. I don't know if I can do it tonight, honestly, because of the fact that I have to leave immediately from here to go to campus, because I have a lab actually for the second astronomy class that started. It's a late start. So I probably will do it hopefully by tomorrow. Here is your task, Susan, then. If you don't see it by tomorrow morning, please send me a message, okay, by like 9 o'clock or 10 o'clock. That's your task now. Okay, very good. Thank you. So we have a deal now. Okay, so I'll work hard on my end so that I don't get a reminder. Anyway, so we are in week 5. We have covered quite a bit of materials up to this point. We went through a lot of things. We discussed basically how we locate objects in the sky. And we came up with terminology basically for the celestial sphere. And we were able to locate objects in it. We came up also with definitions for the time and how we measure time in astronomy, things like that. We came up actually with the current models, basically the best models that we have for the solar system, and came up with 3 laws of Kepler, and they explain basically the motion of the objects in the at least in the solar system. So we came a long way. We still have quite a bit to finish this. We still have actually 2 units are part of the first exam, namely units 34 and 35. Those we're going to introduce today, so we should be test ready as of today. However, usually what I do, I give a practice exam so that you guys will have a chance to also prepare for the exam. The exam is, I'm hoping to avoid Thursday as much as I can. And because I will see if it's going to be probably the 20th of this month, which is this coming week from today, or if it's not possible to do it on the 20th, we're going to jump it to move it to the 27th. However, understand in either case that we will be covering materials past this exam. So chapters, the units that come after unit 35 are not going to be part of this exam. They're going to be part of the next exam. Make sense? Sounds good, guys? Okay, very good. Here is the thing. So I'm going to try to work on the review as soon as possible. If the review is published, you receive it by the end of tomorrow, by the Wednesday, the day before our next session, live session. Then we should really have the exam on Tuesday. That means the review will be due by Monday, by the end of the day. Then on Tuesday you will have the exam. In which case we will not basically do the live session on that day. Now, if I can get the materials ready for you guys by tomorrow for some reason or the other, then we're going to have the exam on the 27th, and we keep on covering the other units that come after that for the next exam. So that's the plan for basically in terms of what we have. Also, let me look at the week in here to make sure that I have the materials before me. Okay, let me share with you the screen, okay, because it's important that we are all on board as far as what we have to do. Share. Before I do sharing, let me first of all make sure I'm in the student view. Sorry about that. Hold on, okay? Okay, by the way, if there is some problem with my camera right now, I think it's a problem. If it hangs, please don't leave, okay? So I will restart it and hopefully we will continue the session. So let me go back into it and make sure I'm in student view in here, student view. Okay, so now I can come back to Zoom and start sharing share. Again, this is your class. This is week 1, we don't need it. Week 2, we don't need it. Oops. Week 3, we don't need it. Week 4, we don't need it. And this is week 5. The reason why I brought up this thing in here, in addition to the quizzes that you have, which are actually part of your preparation also for this exam too. So please take care of them. Make sure you're doing the discussions. All of these things are part of the routine that I'm hoping all of you now by now have basically noticed. There is a new type of assignment that you didn't see before, okay? So this is a project that is due on October 29th. When it says October 29th, it doesn't mean that on October 29th I start working on it. It doesn't even mean that on October 28th I start working on it. As a matter of fact, not even October 20th when I start working on it. That's too late, okay? There is a lot of work that needs to be done before that, and it's actually a timely work that needs to be done all the time until reaching to that limit. By the time October 20th, I would expect you that you're completely done, okay? Your report is done. So let me click on it to show you what I'm talking about in here. It has the instructions in here, okay? What you have to do. It has actually a little bit of also background information about the moon phases. And this is what I'm talking about in here. On September 20th, which is Tuesday from today. So it's a week from today, okay? You're supposed to go out and do observations, okay? On a specific time of night of the dates below, you need to record your observations of the moon on the shape and position in the sky, approximate. I don't need the exact numbers, okay? Meaning, is it to the south, southeast, north, northwest, however you see it in the relative to what you are. You need to know where your north is, okay? And you need to know where your east is and where your west is and where your south is. Is it next to the horizon or above the horizon, almost to your zenith, okay? So somewhere, or is it smack in the middle? So basically, if you're using angles, is it 0 degree, or is it 90 degree, or is it 45 degree, or closer to 30 or something? You don't have to give me degrees. All I want is just approximate positions. If it is too cloudy, make observations the following night. So here is the deal. On the first observation is actually Tuesday, a week from today. Okay. And that is where you're going to report the shape of the moon on that day and the phase of the moon on that day. It may not be necessarily nighttime. It may be early in the morning when you have to do your observations. So you really have to do outside. So you're going to actually put the date. The reason why it's still open here for the date is because it may be the weatherman is telling you September 20th is not is going to be cloudy or rainy or something like what we have recently. Then probably the reminder is that you go first on the 19th. Okay, you will receive notifications from Canvas telling you that tomorrow is your observation. It's a good day to go and spot the moon tonight. Okay, so that you plan. Document that observation, that initial observation. Just in case, if it fails on the 20th, you have your plan, which becomes your observation. Okay, then if it's cloudy on those 2 days, then at least you have a chance on the 21st. Okay, and I'm hoping by then you would have located it. Is it in the evening? Early evening, that is it late in the at night? Is it early in the morning? You're going to find it in the sky somewhere, okay? One or the others. Is it after sunset? Is it before sunrise? So that's basically what you're doing in here. Or is it like well after sunset, like, for example, 10 p.m. or something when the moon starts to rise or something like that. So you're going to do your best judgment to make a observation of the moon on that date. The next observation after that, the second observation after that is the 28th. This is what I was talking about earlier when I said that if you wait to the 29th of October, you missed your project because it starts on the 20th when you have to do your observations. So on the 28th, which is a Wednesday, the following week is when you're going to go out also at night, early in the morning, late at night, whenever you find that the observation is possible. Again, you're going to plan on the 27th to go out actually and do your observations. It doesn't have to be completely out. I mean, try to find a little bit of a place where there is a clearing, I mean, away from the mountains and the trees and things like that, and do your observation, do your best with it, okay? Or tall buildings, if you happen to be in downtown, that's going to be a problem. So you really have to drive a little bit in and out or find a way to get out of those tall buildings. Again, the 27th, the 28th is the actual observations. If need be, the 29th also is another potential observation day. Again, you're going to do the same thing. October 6th, which is, what day of the week is that? Is that the Thursday? Yes, it is. It's a Thursday. October 6th is your third observation. Again, plan on October 5th and October 6th and October 7th, if need be, depending on the weather, okay? The last observation is on Wednesday, actually, October 12th. The last one is on October 12th, okay? You know what? I really don't have time. I'm on a hurry. I have a dog to feed. I have cats to worry about. I have stuff to do. I have a car to take to the mechanic. I don't have time to read through all of these things, okay? Or read the book or do anything else. So what should I do in this case? Well, here is a solution to you. You're going to follow the rubric, okay? You're going to just look at the rubric, what it says, okay? There are questions in here that I need to answer first. Question 1, and here is how question 1 is going to be marked for you. So if I find question 1 and I answer it and it's correct answer, then I'm done, okay? Same thing, I have question 2 also that I need to look at and answer it too, okay? And then I do my first observation, which is on this date. Then my second observation. So this is a rubric of how you're going to receive full credit for your assignment. Observation 3, those dates, observation 4, and finally your conclusion based on your observations and what you have seen basically in terms of the moon phases and throughout this month and so on and so forth, and the position and the location of the moon and how it changes shape depending on the beginning of the lunar month, the end of the lunar month, and so on and so forth. Basically, this is actual observation. You're not looking at the book and answering this question. This is based on your observation. Again, similar to the lab for those sitting in the lab. You're going to upload text in here, or you're going to upload a file. Okay, here is the trick. Part of these things is asking you actually to draw things, okay? For example, for the first observation, daytime drawing, description of the shape of the moon. So you're supposed to draw the shape of the moon too. So now if I do text entry and I'm here trying to answer that question, which is observation 1. Of course, I did question 1, I did answer question 2. And question 1, question 2, by the way, question 2 also has some drawings too. So you have to be careful of that too. Here is question 2 so that you know. Question 2, in the 4 boxes below, and again, it's showing you boxes, but it's not showing them in here because it's relying on this PDF file or this Word file. I'm going to show you this, how these files look like also. So the point being in here is that you're supposed to draw the shape of the moon on those things. So you're supposed to include pictures. That's what I'm trying to say. So you insert pictures in here, and all of a sudden you're going to have a, okay, let me see first of all if I can find pictures on my computer. Okay. Let me first of all find something in here to upload. Okay, where is my astronomy class in here? You know what? It doesn't matter. Let me pick up this folder in here. It says a bunch of things. So I'm going to upload them. Obviously, upload, or not all of them, or just one thing, just to show you how you do the pictures in here. Okay, if I can find the picture in here. Obviously, no. Since we have the lab, trying to find a file for you guys to show you how you can do a file upload. And I'm trying to see. No, that's not it. Does this one include for pictures? No. Okay, I have a picture of Lawrence in here. Okay, so here's the trick. So I need to include a picture in here. That's the point I'm trying to show you guys how to do it in here. So what you got to do in here is that you come in here and you're going to look at this link, upload an image. So instead of doing that, what I'm going to do is drag a picture in here and upload it there. So I have a picture in here. I'm going to drag it and drop it in there. Another way is to simply click in here. So this is actually, it looks like it's a formula, but it's actually a picture. So I'm going to submit it. And there I have my drawing. So this is a picture. As you can see, actually image options. So I'm going to rescale it if I want to. It looks like it's a formula, and it is. After I wrote this formula, I basically took a picture of it, and then basically you have an image in here. As a matter of fact, if I look at the image it's a .png formula. It's a .png picture, so which is a kind of picture also. So the point being in here is that your drawings, you can do them, take a picture of them with your phone, and then upload those pictures in here, just to show you that you can do a text upload. If you don't want to do that, you can do actually a file upload and drag the file and drop it in here, or browse to it from here. Okay, click in here and browse to it. Let me show you those two files because they are probably going to be helpful to you to do them. This file is a PDF version of this very same file. This is a Word file, and this is a PDF file. Whichever is easy for you to work with, your file. So I'm going to click on the PDF file and open it. And actually, you know what I need to do in here? I need to save it to my computer because there is an issue. I'm going to tell you exactly what it is. This is a fillable PDF file. That means you can fill stuff on it. Right now, I don't see how I can do it using this browser. So what I'm going to do is, and it's called Moon Phases Form. So I'm going to download, click on download, and then open. I don't want to open it in the browser. Okay, when I opened it in the browser, apparently now it's let me to fill it. Are you guys looking at this file in here with this shaded area next to the name? Yes, no? Are you looking at something that says Astronomy 120, Fall 2020, Moon Phases, and then the name in here that they can put stuff in it, like my name, for example? It's not right. Are you guys looking at this or not? Yes, no, maybe? Okay. Okay, very good. Thank you very much. So since you guys are looking at it, I assume that you guys can actually do the same thing. You don't have to do it with the browser. For some reason, it's working on this browser. In the old days, you choose not to work on browsers. You have to open it with the PDF reader, normal PDF, which is a free software, okay? But the browser nowadays is a PDF reader. You can fill it, but don't forget to save it when you're done, okay? Because if you don't save it, everything you write in it is gone. So it's a good idea to click on save so that you save the file. So the first question is asking you about, here is the moon going around the earth in positions A, B, C, D, and E throughout the lunar month, okay? The sun is in one position, the earth is in one position. You're looking at this moon phase, which is a crescent, okay? And you're asked to answer the question is, would this correspond to position A, or position B, or position C, or position D, or position E of the lunar month? Okay, so just by looking at this one, you're going to be able to tell me, are we toward the end of the lunar month, or the beginning of the lunar month, or sometime immediately before the full moon, or just after the full moon, or a quarter moon. So basically, that's what you're deciding, and what quarter it is. Okay, so that is, in looking at this picture, you're going to make a call on it. Okay, that's one thing. If not, if you have difficulty with this question, please let me know. I should refer you to the unit that you're supposed to be looking at it, and the unit is unit 8. Should be able to help you with that, okay? So again, this is the question. Which of these positions, okay, it's not working, so I'm gonna save it to my computer, and I'm gonna save it to here. And come back and open it from there, because it's supposed to help me basically fill out these questions in here, and it's not doing that. So I'm going to stop sharing, and I'm going to open the file with the normal Adobe Reader. And when I do that, oh, it saved it. Okay, when I do that, I'm going to share it with you guys so that you can see exactly how this works, okay? So here is the file. I put my name earlier, and if I'm working with somebody else, it's not a good, you are required to put the other person's name, okay? Other person. And that's actually a good thing to do, because you see that as I'm typing, the character starts to stop. Are you guys looking at the PDF file, yes or no? Are you guys looking at the PDF file? What are you? Okay, very good. So let me go back to it. Okay, again, this is the information that was actually on the same website. And now when it tells you to look at the picture below and do all of this stuff, so it's referring to this file in here. Okay. I'm supposed to answer this question. For some reason, it's not showing me. I'm going to fix this file. Okay, it's supposed to be a fillable file. It's not giving me a place to fill it. So for some reason, it's gone. But here is the next question. In the 4 boxes below, sketch the shape of the moon and how it would appear in the 4 phases and so on and so forth. So basically, if you choose position A in first question, then you're supposed to draw pictures for B, C, and D, and E, and how the moon would look like, and label them. So if I chose A in the first question, this is for B, and then I'll have to draw a picture and then upload it in here. Same thing in here. When I double click on it, it gives me the option to browse to the picture and find it, and then upload it, okay? And then I do C here, oops, C, and then I do D in here, and E in here, okay? So that is how this is supposed to give you the, so it's the same thing as you can do with the text entry in the project when it's due. You can do it actually with a PDF file. Okay, upload the pictures in here, and they will be organized in such a fashion that you will have them in here. Again, take a picture, call it B, whatever you want to call it, then upload it to this location and make sure it's properly labeled. That is if it's A. If my answer to the first question is A, if my answer to the first question is C, that means I have to draw A, B, and E, and D, okay? So this will be A, this will be B, I'm sorry, A, C, D, and E, because I decided B is the correct answer, or whatever answer you decide on the first one, you need to draw the other 4, okay, because you have 5 in here, okay? So that's the second part. And then you're going to do your observation on around September 20th, because it's kind of ambiguous at this point. It may be September 19th, it may be September 20th, it may be September 21st. You're going to put the date in here, and you're going to put the time in here. Was it in the morning? Was it in the evening? Was it later in the at night? And so on and so forth, okay? And in here, you're going to, the shape of the moon. Was it a full moon? Was it a, I'm sorry, yeah, the shape and how it looks like. So you're going to give a brief description on that day. And then in here, you're going to name the phase. Half of the moon in here was lit, and so on and so forth, and the other half was not, or the whole moon couldn't find it. There is no moon, so I suspect it's a new moon, or it's a full moon. the entire moon is covered on that date. And then in here, you're going to describe it. And again, you're going to draw a picture in here. You're going to upload it. On the 28th of September, you do the same thing. On the 6th of October, you do the same thing. On the 12th of October, you do the same thing. And here you draw your conclusion. For some reason, I couldn't. So let me fix this one quickly in here. Can I fix it? No, can't. It's still. Anyway, so I will fix it and send it back to you guys, upload it back, because in here you're supposed to have a field that you can fill for question number 1. Does this make sense to you guys, this whole project? At least in principle. I know that there are some technical things that's probably going to ask later on. Make sense? Okay, very good. Very good. Thank you, guys. Okay, so that's something that I wanted to make sure that you guys are on board as far as this part in here and that you're ready for it. And it's going to start next week, and you're going to be receiving reminders, one on the 19th and one on the 20th, and another one on the 27th and the 28th, and so on and so forth, until you're done with the project. So make sure that you are ready for them. Okay, Canvas is the one that's going to be sending you that. Okay, I think we spoke a little bit about this project in here, which is important for this. It's part of your grade, by the way, part of your overall grade. Okay. Okay, let me go back into Canvas in here. Share Canvas. Again, the stuff that you do on the report itself is similar to what you do in here, with the exception, as I was saying, that you could actually, let me go back here. You could come in here to the Lunar Observation Project, and you can insert below, following the steps in here that I was talking about in here. And when you're done, you just submit your project. Again, as I was saying, don't start on October 29th, because that will put you way outside of the window of doing the actual project. The actual observations start next week, okay? So this is item 1 from that, and let me go back one step in here to see what the week look like. Again, you have 2 quizzes for this week. You have also the discussion, and you have quite a few other items in here that are going to be due. So those are the stuff from the week before and the homework assignments from the week before, okay? So that is the things that you have in here and the ideas behind units 34 and 35. So let me stop sharing and let me get into the PowerPoint, unless you guys have a question for me. So let me get into unit 34 and go back into Zoom, share unit 34. Okay, so basically we're going to look at the main features of the solar system. I know we talked about them before, but today we're going to actually formally introduce them. You have the sun, which is one of its main features. It's actually the main feature. More than 99% of the mass of the solar system is the sun itself, okay? Then you have the planets, and the planets are divided into 2 different kinds of planets, rocky planets, like the Earth and Jupiter and, not Jupiter, I'm sorry, the Earth, Mars, and Venus and Mercury. And then you have the gas giants that include, of course, Jupiter, Saturn, Uranus, and Neptune. And in addition to that, you have the moons, also part of the solar system. And then you also have the dwarf planets, and each and every one of those dwarf planets, at least a lot of them, do have moons also. As a matter of fact, we also have asteroids, and some of the asteroids actually have moons. In addition to that, we have the Kuiper Belt, which is sitting outside of Neptune. And we have way outside of the Kuiper Belt, we have the Oort cloud, in addition to the comets. So these are the main components of the solar system. The solar system has some features where all of the planets orbit the sun in the same direction, and also they spin around their axis more or less in the same direction, with the exception of one that is spinning backward, actually internally, namely Venus, and one that is spinning on its head, namely Uranus, but everybody else is spinning in the same direction. Some of them have tilt. One of them has a lot of tilt, and namely, first of all, Venus is upside down, and then one of them is on its side, named Uranus, but others, they have tilt. Some of them don't have actually much tilt at all. So those are the some of the features of the solar system, and the planets, all of them, and their and also the asteroid belt, and even the Kuiper belt. They're sitting on the same plane, namely the ecliptic plane where the sun is. The objects that are outside of the of that, namely in the Oort cloud, are not. They're kind of a spherical shape, basically, and they are very far away from the sun. So this is basically the main features of the solar system. There is a line between Jupiter and Mars, and that is called the frost line. And that is the line that separates the when water basically freezes, and below that when water basically exists in the liquid form on its own, because the temperature is high enough for it to exist in the liquid form. And that is actually also one of the features. As a comet is coming from the Oort cloud or even from the Kuiper belt, it's approaching the sun. By the time it crosses that line, it starts to basically the ices in it, which is water ice, or some of them methane ice, and all of this icy stuff in it, starts to melt, and the comet develops a tail. And as it goes around the sun, that tail also starts to grow until it reaches the sun. It's going to shrink until it passes that line back again, and then it becomes a rock again, and then continues in its orbit around the sun in this fashion. So those are some of the features of the solar system that we know of, okay? So this is basically what we'll be discussing. And then let me share with you something in here to give you an idea of how that looks like. Let me share Universe Sandbox. I don't know if you have seen this one in here. I'm very far away in it from the sun. As a matter of fact, even Sedna at this point, this is the orbit of Sedna, by the way, which is extremely far from the sun, is visible. If I move further away, then it's really I'm very far away from the sun. Even at this distance, we are still near in the neighborhood of the sun. This is where the Oort cloud is. So if I come closer again, the main object of the solar system by far, of course, is the sun. And I don't want to get too close, otherwise the screen becomes too bright. So this is the sun. By far, it's the main thing in here of the solar system. Then you have, of course, Mercury, which is the closest object from the sun. Then you have Venus, which is the third object that is close from the sun in terms of big, massive objects. And then you have Earth. So the Earth is the third object that is close from the sun. Look at the plane on which they exist. This is the ecliptic plane, because we need to go through Unit 35 and explain why is that so. It's important to understand how is that so, okay? Then if we keep on going, we have, of course, Mars, and that is the end of the inner planets. So this is the first division in the solar system. Between Mars and the next planet, which is Jupiter, there are a bunch of objects in here. You see Vesta, you see Ceres, you see also Iris, you see Hygeia, you see all kinds of objects in here. And those are part of the asteroid belts. They're small objects for the main part. Some of them are big enough to be considered dwarf planets, like, for example, Ceres, but and there is actually a mission to it too. So Ceres is actually a big enough object to be a dwarf planet, but that's between Mars and the next big planet, Jupiter. By the time we reach Jupiter, we are 5 astronomical units from the sun, meaning the distance between Jupiter and the sun is 5 times the distance between the Earth and the sun, basically, okay? Slightly more, but that's in a nutshell what it is. So the frost line I was describing earlier is somewhere between Mars, which is in here, this orbit of Mars, and the orbit of Jupiter, okay? So the comets, as they approach the sun, once they cross that line, they start developing a tail, okay? And that tail becomes visible more and more as they approach the sun. And then as they pass by the sun, the minute they cross that line again, by that time they freeze again and they become a rocky object. Because again, this is the line where the ice melts when you're close by, or freezes when you're on the other side. Then after Jupiter, of course, comes Saturn, and Saturn's orbit is actually almost twice as far from the sun as Jupiter is. So now we're looking at ridiculous distances. And even further than that, you have Uranus, and even that, after that comes Neptune. All the other objects that you see, including Pluto, including Sedna I was talking about earlier, Quasar, Haumea, Makemake, all of these objects, they are dwarf planets and they exist in the Kuiper Belt for the most part, okay? So this is the Kuiper Belt. It has far more objects in it, the Kuiper Belt, okay? So they have a lot of objects in there. And then, of course, that's the extent of the solar system, at least that we know of. Then the hypothesis was made for the Oort cloud by Oort himself, and at the end, it was actually shown that those comets can only be coming from further away regions of the solar system, and those are the extent of the solar system. So this is, in a nutshell, how the solar system would look like, and these are the main features of the solar system. Okay, so. Then describe the typical orbit. Again, we described we saw Kepler's laws, and these are typical. It's not just true for the planets; it's true also for the dwarf planets. It's true also for even the satellites of the planets, namely the moons. Also, they follow Kepler's laws. They have similar orbits. For the most part, as I was saying, all of the planets orbit in the same direction, and with kind of a little bit of oddity. And we need to explain those exceptions based on how the solar system formed and what happened to it immediately thereafter, okay? And then there is a critical quantity in here that we talk about usually, and that is the density, okay? What is the density in a nutshell? Okay. If I take a given mass of an object and another mass of an object, they may or may not occupy the same volume. Or if you wish, if I take a volume of an object and another volume of a different object, they may or may not have the same mass. They may or may not weigh the same. Obviously, if I take a 1 cubic meter of a material of air, for example, it weighs a lot less than 1 cubic meter of water, which should weigh less than 1 cubic meter of iron, for example. So, and which should weigh less than 1 cubic meter of lead, for example, because it's denser, or aluminum, which is even, which is lighter. I was thinking uranium, or gold, for example. But aluminum, actually, 1 cubic meter weighs less than that of iron. Okay, it weighs more than the water. And in case in point, you can take aluminum and put it in a bucket of water. It's going to sink. Okay. But it weighs less than the iron. So this is a characteristic of materials, regardless of where the material is, whether on Earth, whether on the moon, whether in your lab, whether in somewhere else. Under the same conditions of temperature and pressure, the material will have a unique density. It doesn't change. Okay. And this is a useful piece of information, because if I look at the density of a planet, basically how big it is, physically speaking, what's its volume, by just finding its diameter, because the spherical object, its volume depends only on the radius, which means the diameter is the same thing. Okay, the radius is just half the diameter. So if I give you the diameter, you know the radius, and vice versa. So there is a geometry formula that you probably have guys seen, and that gives you 4/3 times pi times the radius cubed. So if I know the radius of a planet, I know its volume. Okay. Then, if I know its volume, and if somehow I can find its mass using, for example, Kepler's laws, then I know its density. Because all I have to do is take the mass of the planet and divide it by its volume. Once I know the density, I can tell the structure of that object. Isn't this fascinating? I'm always amazed into how simple some of these things is. I can tell what that planet is made up of just by measuring its density. If it is 5.5 grams per cubic centimeter, for example, for the case of the Earth, we know the Earth is mainly made out of materials that are heavy, like iron and nickel in the core. And as you go upper and upper in its layers, you're going to find silicates, which is basically rock and things like that. A planet like Mercury, for example, has a density of 5.4. So it's also has a similar structure. Planet of Venus has a little bit less density than both the Earth and Mercury, but it also has a rocky structure. Same thing with the Mars, and the same thing with the moon. So just by looking at the density, the moon has a little over 3 grams per cubic centimeter, but it's dense enough. Okay. So now I have an idea of what makes up the moon, what makes up Mars, what makes up Venus, what makes up Earth, and so on and so forth. Then if I do the same density, for example, comparison for the case of the outer planets, I'll find them less dense. Jupiter is slightly denser than water, 1.29 kilogram per cubic centimeter. Okay. Whereas actually, sorry, 1.29 grams per cubic centimeter, 1.29 kilogram per cubic meter. That's the distinction here. Yeah, or one. Anyway, it's 1.29 grams per cubic centimeter. That's an easy number to remember. So it's slightly denser than water because the water has 1 gram per cubic centimeter. For Saturn, it's actually less than 1 gram per cubic centimeter. In other words, if you take Saturn as a planet, and if you can find an ocean big enough that can hold it, it's going to float. That's the only planet that can float. As a matter of fact, if you go through the density of all of the planets, you will find that the Earth is the densest planet in the solar system. Of course, the sun is less dense than those because it's made up of mainly gas. And again, the structure can be dictated from the density. You could tell what an object is made up of just by playing around with this thing. So if you take how much iron I need to put, how much nickel I need to put, how much this material I need to put, how much water I need to put, do I get 5.5 grams per cubic centimeter? Sure I do. Then in this case, this is Earth. Then I know its composition. Obviously, it's not as simple as that, but the point being in, it gives me a good idea of what makes up that object. And this is what we're doing actually with exoplanets too. When we look at exoplanets and determine their mass based on how they orbit or other objects orbit them, or depending on their period and so on and so forth as they go through the planet. And if we can find their size as they, for example, pass in front of their host star, knowing how fast they move, then we can use Kepler's laws to find how far they are from their host star. Then we can find their size. Once we know their size, then we have their density. Since we know the density, then we can tell that exoplanet is made up of so and so and so. Does it has a lot of water? Does it have a lot of water? So basically, we can do a lot of decisions based on that. It is really amazing what you can learn just from the density. That's why it's an important property that we need to explore in here. Okay. So again, this is an introduction. Again, this is the slides that you guys have. I hope that you guys are doing the reading nonetheless. You're not relying on this presentation. Okay. Again, in terms of size, as I was saying, by far, okay, the sun is the biggest object in the solar system. And then if it were not for the sun, you have Jupiter that basically outweighs all of the other planets combined, including Saturn. Okay, then comes Saturn, then the other basically two ice giants, namely Uranus and Neptune. And then the small dots that you're looking in here, those are actually the rocky planets. The biggest rocky planets in the solar system, of course, is the Earth, which is slightly bigger than Venus, which is next door to it, and then far greater than Mars, followed by a tiny planet, namely Mercury, which is the closest planet from the sun. Mercury, as a matter of fact, is so small that it's lighter than even 2 other moons. Okay, as a matter of fact, it's comparable to the size of about 4 moons altogether. Okay, I mean, it's slightly smaller than 2 moons and slightly bigger than 2 moons. So that's basically, it fits right in between them. Okay, so that's basically how the solar system, the main features of that. In addition to that, you have dwarf planets. I mentioned Pluto, which is part of the, it's a TNO, trans-Neptunian object, mainly past Neptune. And then you have Ceres, which I mentioned already as being an asteroid belt object, basically part between Mars and Jupiter. And then you have Eris. Eris is actually another planet, another dwarf planet that is actually in the Kuiper belt also. And you have Makemake, which is part of the same region. Those are just few. I mean, I have some dots in here because you have Haumea, you have Sedna, you have a bunch of other things. Quawar, you have other things also in here. So it's not just those two, those three basically objects. If it were not for Eris, Pluto would have continued to enjoy the status of probably of a planet. But because of the discovery of Eris and other planets, Eris is a little bit more massive than Pluto, although it's smaller in size slightly, but it's more mass. So Eris turned out to be really the thing that basically damaged the basically the status of Pluto in astronomy. It used to be considered as the 9th planet, and then because of the discovery of this planet and these dwarf planets and other dwarf objects in here, Pluto was demoted and classified with this group. Okay, so this is basically some of the stuff again. This is the Kuiper belt. The Kuiper belt sits on the same ecliptic plane as I was describing in here. It has a lot of objects in here. I'm sorry, this is the asteroid belt. This is the asteroid belt because I see in here a series in it, but this is the Kuiper belt. The Kuiper belt is well past Neptune, okay? It's outside of Neptune. So that is the Kuiper belt, and this is the asteroid belt, and both of them are similar basically in structure, at least in position. The structure is different. This is more icy, this is more rocky. Okay, that's in a nutshell what the big difference between them. Because this is just on the I mean the frost line passes probably around its middle, but this one is way past the frost line. So all of the objects in here are frozen solid. Because Pluto itself is frozen solid for the most part of its time. I mean, you have to have elements that can evaporate at very low temperatures for it to have an atmosphere of some kind. And this is the story of basically Pluto, okay, and more TNO objects. So that when you see a TNO in here, it stands for trans-Neptunian objects, meaning anything past Neptune, okay? One of the interesting objects in here that is kind of is the moon of Neptune, Triton. Triton itself used to be actually a TNO that was captured by the planet itself, and now it's one of its moons. It's actually the biggest moon there for Triton, and it is actually also part of the dwarf planets that formed in the part of the Kuiper belt objects that were in there. Okay, we're going to go through this one. We're going to see how Triton was captured by Neptune, or at least how we think what happened to it. Okay, then way outside of that is the Oort cloud. Okay, and this can extend all the way to 50,000 astronomical units from the sun. We're talking ridiculous distances. The blue line that you see in here, that's the orbit of Neptune. And this is very, very far away from the sun. This is 30 astronomical units. So from 30 to about 50 astronomical units is your Kuiper belt. And from 50 astronomical units to about 50,000 is basically, or even more than that, 100,000 in here, according to the scale, you have the Kuiper belt. So it's a huge structure. I mean, this picture doesn't give it, it's not to scale. It doesn't give it justice. It doesn't do it justice. So it's big. I mean, it's super massive object, I mean, structure. And that is where objects like, for example, comets, they come from, for the most part, they come from that region. Of course, some of them, depending on their period, if they take a long time to come, those are basically coming from the Oort cloud. No way, they could come from anywhere else. The short-lived, the short period comets, they must come from the Kuiper belt. The reason is because those are relics, all of these objects are relics from when the solar system formed. These comets, because of the way they evaporate when they approach the sun, then they should really have dissipated a long time ago. Unless their period is so big, then they're still in the process of being evaporated, but it's still, the time did not lapse that long, because they take a long time to go around the sun. This is the hypothesis for the Oort cloud, and that's kind of how it's justified basically in it, okay? One of the objects that we're looking for, which is Planet 9, it's hypothetically is in this region, maybe not that far, but at least in the Kuiper belt, okay? Namely the Planet 9 that we think exists. And we're going to talk about that and the rationale behind it. Why is that? Okay. So, so again, forget about this outer objects in here, the TNO objects in here. All of the other objects, they orbit the sun more or less in the same plane. And it has to do with the conservation of angular momentum. So the key concept in here that comes from mechanics is angular momentum. The same thing, a ballerina, for example, spinning and brings her hand and spins faster and pulls her hand out, she's going to slow down. And the same thing that causes a rubber duck, for example, going to spin faster when it gets closer from the sink, or is going to move slower when it's further away. That is the same reason for it, which is the conservation of angular momentum. To go an idea of why is that so, it's because probably, not probably, because when the solar system was going to be unit 35, when the solar system started to form, as it started to get closer and closer to each other, together, obviously, if you lose kinetic energy and you gain potential energy in this case, and I'm sorry, you lose potential energy because here is the thing. The objects are far away, so you have a lot of potential energy. As the objects get closer and closer, it loses potential energy. What I mean by potential energy is the following. I have a pen in here. It is sitting still doing nothing. If I pull it up, I gave it potential energy. How do I know that? If I let go of it, I'm going to lose that potential energy and convert it into kinetic energy, energy of motion. So that's what the kinetic energy is. So indeed, if I let go of it, now I lost that potential energy I gained by putting it up. Now, if I let go of it, that potential energy is going to go and be converted into kinetic energy. The same thing happens in the solar system. When the objects were far away, they had potential energy because the energy of gravitation. They're pulling on each other, but they are far away. If they come closer to one another when the solar system starts to form, in order to form the sun, among other things, the gas that was there and the dust that were there starts to accumulate and get closer and closer. So now it's losing potential energy and converting it into kinetic energy. So in this case, they have to spin faster and faster. And that spinning, that kinetic energy will ultimately change into actually heat, different form of energy. That's what caused the sun actually to heat up in the core to a point that actually nuclear fusion took over, so that the sun produces energy using nuclear fusion, fusing helium with, hydrogen to form helium. So that is basically what happened to the sun. In the same fashion, because there is nobody steering the sun, there is no external force causing it to spin up or slow down. So the only thing that is causing it to do this one is this mechanism as I was describing, and this is an internal process. Because it's an internal process, there are no external torques, basically. Nobody's spinning, like, for example, when you're trying to turn left or right, you come take the wheel and you spin it one way or the other. This is a torque. You exert a torque on the wheel. Nobody's taking the whole solar system and twisting it one way or the other. It's an internal process. Because of that, the angular momentum must not change from whatever it was before, when everything was moving slower, to now when everything is moving faster, trying to get closer together. So the angular momentum is conserved. It has to do immediately with the torque. The fact that you have zero torque, meaning that the angular momentum should not change. The angular momentum is a vector. So not only they were getting faster, but they stay on the same plane. That is the direction of the angular momentum. The direction of the angular momentum is perpendicular to the plane, forcing everything to stay on the plane. You take a piece of dough, for example, when you're forming a pizza, and you spin it, and you keep on spinning it like the dough maker is trying to make the pizza thing. At some point, it's going to start to flatten. It's going to flatten, and because you're spinning it faster and faster. That's exactly what happened to the solar system. So think of it as a big dough of material that was existing before in our region where the sun is right now and where the planets were. And then as it starts to come together and spin faster and faster, and as it does, it flattened until its point. In this case, you have the ecliptic plane. So this is basically, in a nutshell, what this picture is talking about. Now you're saying, what in the world is going on with these tiny objects in here that are moving outside of Neptune? Well, the TNOs are so small that their paths can be disrupted easily, okay? That's exactly what happened to them. You have Eris, even Neptune, even Pluto, itself is a little bit off. As a matter of fact, even the planets, they're not exactly in the same plane. Some of them are on and off, because immediately after the solar system formed, they get into collisions with one another. There were other planets that existed in there. They got into either thrown off completely off of the solar system. Some of them were thrown into the solar system and collided with other objects, causing all kinds of disruptions in this picture that I was describing to begin with. And among other things, also flipped some of them. Like, for example, Uranus is actually sideways, and actually Venus is completely upside down. Earth was tilted a little, 23.5 degrees, leading to the formation, among other things, the moon. Okay, so that's basically what happened to them. Again, all of the planets, as I was saying, have a tilt. I'm sorry, that same process caused all of the other tiny ones to be completely thrown off basically that plane, okay? As I was saying, some of them have tilts, like for example, the Earth, 23.5 degrees. Mercury has absolutely no tilt, okay? The sun itself is a little bit tilted. The Earth is 23.5 degrees. Mars is very close from the Earth, actually. Its tilt is 25.5 degrees. Okay. Ceres is barely tilted. Same thing with Jupiter, but Saturn is tilted in the same fashion. As a matter of fact, sometimes the rings will be very visible, but sometimes when it tilts back this way, you're going to basically lose the sight of the rings, because they're going to be within the line of sight, and you're not going to see them. Obviously, the process takes a long time before it changes, because the seasons on it take a long time to complete. Okay, so it's not like the seasons take only 1 year. I mean, 4 months on Earth. Then you have Uranus, as I was saying, it's spinning upside down. The North Pole is pointing to the sun at some point, and when it's on the other direction, it's the South Pole actually pointing to the sun. And the equator is actually it's polar regions, because it has slightly over 90-degree flip. Then Neptune, which is not too far from the Earth and Mars, and the other objects, we don't know how tilted they are, because they're too small and they're actually far away. I didn't talk about Venus in purpose because it's flipped backward. 177 degrees. It's like you take this object and you put it backward. You take a cup of water, for example. You hold it and you spill it completely backward. That's why the day on Venus is actually backward. It rotates in a different fashion. The sun rises in the west and sets in the east in Venus, while it's spinning in the same direction as everybody else. You see what happened in here to some of these objects in here? The biggest, basically, problems during the early formation of the solar system happened to Venus and Uranus. Everybody else is more or less in the same direction. Actually, Pluto also. Pluto is tiny objects. Those tiny objects, you really don't... I mean, all kinds of things could have happened to them. For all we know, probably Pluto was turned 2 times before it settled in that position, because it's too small. Okay. As I was talking about earlier, we use this formula to find the volume of a spherical object. Okay. So if somehow I can find the distance, and if I can find the angular size using the formula that we have seen from previous units, that are, I think unit, what is it, 11 or something? Yeah, we can use that to find the radius, the diameter actually. Once we find the diameter divided by 2, we have the radius. We use this formula from geometry to find the volume V. And if we somehow can find the mass of a planet, like for example, Venus, this is one of our labs in Astronomy 125. In Astronomy 125, we're going to measure the mass of Mars, okay? The way we measure the mass of Mars is by observing the time it takes for one of its moons. Actually, we're going to monitor Io every 6 hours and see how it goes around the planet. Okay. Based on that, we use Kepler's laws to find its mass, and then from there we're going to find its density. Or if we know the density, we can find its mass using this formula also to confirm. I'm sorry, this is the one that we're going to use in the lab. This is the formula that we're going to use in the lab, okay? to find the mass of Jupiter. Take the mass of Jupiter that we find using this formula, take the mass of Jupiter that we use with direct observation for Jupiter, and all of a sudden we have its density. And if we know its density, we know its properties, basically. What is it made up of? What makes up Jupiter in this case? You see, that is really the challenge. So this is, again, it's a fun lab. I hope that at least for those sitting in 125 to enjoy it. The others who are not sitting in the Astronomy 125, the idea is the following. You take one of its moons, we take Io, and basically see how long it takes to go, basically determine its period, okay, by looking at observations over every 6 hours as it goes around the moon, and the moon goes around Jupiter. And we have a telescope actually that we're going to open. It's a 40-centimeter telescope that we're going to use. We're going to request time for it, and most of the time we're given time for that telescope. Hopefully we can get a larger telescope, 1-meter telescope, or even larger, 3 meters. That's being too ambitious. But the point being, in here, you collect data. And as you collect data, you're going to find basically its path. It's going to look like a periodic motion. And after you do that, you're going to find its period, knowing its distance, using the combination of Kepler's law and Newton's basically law of motion. It gives me this formula. From here, I'm going to find the mass of Jupiter. This is how we're going to weigh Jupiter in the lab. Okay. Also, based on observations, we can find its radius. Once we find its radius, we know its volume using this formula from geometry, plane geometry, for the volume of a sphere. 4 times pi. Pi is just a number, 3.14 divided by 3 times the radius cubed. It's divide the two, now you know its density. Then you can go and tell people, hey, I know what makes up Jupiter, what Jupiter is made up of. Imagine this method used for other objects too. It's not just for Jupiter. You could use this as long as you can find a moon going around an object, or a planet going around the star, or a binary system, like 2 stars, for example, orbiting one another. Then this is a very powerful technique to find the masses. If this fails, then other techniques are called for, okay? Other methods of finding masses are called for, okay? And this is actually one of the also part of the labs that we're gonna do for other objects to find their masses and sizes and so on and so forth, okay? Namely stars, okay? But this is the technique that we're going to use actually in the lab. I don't know if it's, I think it's probably 3 more labs before we get to it or something. If not, check the schedule. For those who are not sitting in the Astronomy 125, so I'm hoping that you guys will take care of that sometime in the future. Again, this is just an explanation of what I was explaining. This is the same steps of what I was talking about. Knowing the density gives me an idea of what makes up the planet. Again, we don't really have access to a different planet other than Earth. Earth is a very handy planet, and that's part of our study that we're going to go through in the next few minutes. And actually also now we have put InSight in 2017, which is a lander on Mars. And InSight actually sent a probe several meters, or at least about a meter, into the planet. And now it's also looking for Mars quakes, similar to earthquakes, okay? That will give you an idea also about the structure of Mars. So now we have actually a good model for the planets, how they are formed, what's going on in their cores. Of course, a core of the Earth, for example, is made up of mainly iron and nickel. Those are the 2 heavy metals. And then we think also probably the same thing is true for Venus, although Venus does not have tectonic plates like the Earth does. So for some reason, it's only 1 block basically, and it has a mantle. It has a similar structure in here, but it has silicon because of, again, its density is not too far from the Earth. As a matter of fact, the next largest density in the solar system is that of Mercury, and then the moon also, which is a rocky planet, and so on and so forth. And these are different densities. As I was saying, this is relatively speaking how the Earth compares to the other planets. Jupiter here is slightly heavier than water, and the other 2 planets, actually these 2 are a little bit denser, but this one is less than that of the water. Okay, but now just by looking at these densities, you can basically compare objects. In terms of density, you can compare their structure. You will have an idea of what they make them, how they are made up of. These are models right now of what is inside these planets. but they're confirmed now more or less by the observation of another object in the solar system, namely at least Mars. We're studying it currently. So this is what we have models, because we really were never able to get into any of these structures, but this is probably a good working model right now, based on what we know, which is Earth really. Okay, so so this is actually a description of the sizes and how iron and nickel formed in there. We still have about 15 minutes probably. I don't think we can get into Unit 35 today, but hopefully, because we spent a little bit more time on the project today than anything else. So we're going to finish Unit 35 next week, and then even probably get into the next stuff. And hopefully we will have all of the materials that we need, okay? For next week. Any questions before I close the recording? If not, I'll see you guys Thursday, and hopefully I'll remember to upload the link to the video from last Thursday. And I'll see you guys Thursday. And those in the lab, I see you in the lab too. Bye, guys.